Right, so now we move on to chapter 10, our penultimate chapter, rigorous differential calculus. Now, this is a bit of a strange chapter in as much as you're going to see again, yet again, stuff that you did routinely in calculus in first year, stuff that you've just been told. So I'll have to give you a bit of motivation along the way as to why we're doing some of these things more carefully. Still, we start fairly straightforwardly with the definition of derivative. Now, you can have one-sided derivatives, but we won't be dealing with that in this module. So we're only going to try to differentiate at points where you can approach the point from both sides. And that's why this definition, I insist that A is in the interior of your domain. So your function's defined, it's real valued on some domain. I insist that A should be in the interior of the domain in order to try to differentiate there, because you need to be able to approach A from both sides. So once you've done that, then you can ask about limit of x tends to A of things from both sides. And of course, you look at this quotient, f of x minus f of A over x minus A. Or you could change variable by setting h. You can set h equals x minus A, and then you get this other version, both of which should look very familiar to you as notions of differentiation. And for it to be differentiable there, that limit should exist and be finite. But as far as I'm concerned, the and is finite is optional. In this module, limits must be finite. I'm not accepting plus or minus infinity as a limit anyway. It's different if you're doing L'Hopital's rule. When you're doing L'Hopital's rule, you really want to allow plus or minus infinity to be limits, and so it's a slightly different setting. But for us, when I say the limit exists, it means and it's a real number in this case. And then, of course, you can define f prime of A, and there you are. That's what you've always done. So some things are differentiable and some things aren't. Let's have a look at what the problems could be in a minute. But first, OK, you do this differentiation, and then, of course, you've got this new function f prime, the first derivative. You can do second derivatives, third derivatives, and so on, possibly, if you can go to higher derivatives. But let's focus on the first derivative for the moment. Defined at those points of the interior of your domain where the function is differentiable. Now, I'll just take some open set in R which is contained in the interior. Maybe you'll be an open interval or something. Then we'll say that the function is differentiable on that particular open set if it's differentiable at every point of that open set. And then you can define f prime on the open set and maybe a few more points as well. And if you want to talk about a differentiable function is one that's defined on an open set and differentiable at all points of it. So that's what I mean by a differentiable function. So we've got all the standard examples. From G11 Cal are available. So all the, you've got trigonometric functions are differentiable where they're defined, except for things like arcsine, which has a problem at the place where it becomes infinitely steep. So there are some perfectly good functions. There's another one, square root of x is a nice continuous function. Let me show you that one. Let's have f of x equals square root of x is continuous on the interval on R plus. but it's not differentiable at 0. So it's only differentiable on the open interval 0 to infinity. Why is that? Well, you know what it looks like. It gets infinitely steep at the origin, which is quite hard to do. So here's y equals square root of x. Remember, that's non-negative square root defined for x greater or equal to 0. Still continuous at the origin. As you tend to 0, the values tend to 0, but it's infinitely steep at the origin, and the derivative, that limit, is not finite. And we don't accept derivative infinity. That doesn't count for us. So we say it's not differentiable at 0. There are other reasons why you can fail to be differentiable, though. We'll see some of those in a minute. One easy way you can fail differentiability is if you're not continuous. If there's a jump in your function, then you can't possibly be differentiable. Now I'm going to prove this for you properly, because it's a very quick proof, and it's worth seeing. But a lot of people make the mistake of thinking that the converse might be true. But it isn't true that continuity implies differentiability. We've already seen one. We just saw an example of a continuous function which wasn't differentiable. But I'm going to show you some more of those in a minute. So they are different concepts. Differentiability is stronger. If you're differentiable, then you're continuous, but not the other way around. So here's what we've got. We've got a real valued function defined on some open interval BC, and we've got some point in BC. So I'm assuming B is less than C here, otherwise you couldn't do that. So suppose the function is differentiable at this point, then I want to claim that it's continuous there. And then the second bit follows, because if you're differentiable at every point, remember, differentiable on the interval means you're differentiable at every point of the interval. So if you're differentiable at every point, then you'll be continuous at every point just by using the first part. So suppose then that f is differentiable at A. And what we're going to do, I'm going to prove that the limit as x tends to A of f of x is equal to f of A. That's one of our many equivalent definitions of continuity at the point A. Well, what do we know? We know that the limit as x tends to A of f of x minus f of A over x minus A is equal to f prime of A, which is a real number. So, for x not equal to A, and x should be in our domain, we have f of x minus f of a. Because x is not equal to a, the next thing is not division by 0, so I can just write f of x minus f of a over x minus a times x minus a. I haven't done anything. But now I can use the algebra of limits. This bit tends to f prime of a. This bit tends to naught. And what do we get? So this tends to f prime of a times naught equals naught as x tends to a by the algebra of limits. But now you can just add f of a, and you get f of x, which is equal to f of x minus f of a plus f of a tends to naught plus f of a equals f of a as x tends to a. As required, and we finished. We wanted to establish that f of x was getting very close to f of a as x got close to a. We knew actually rather a lot more. We knew not only that f of x minus f of a was small, but we knew about how small it was. We knew that f of x minus f of a, when divided by x minus a, was quite close to f prime of a particular number. So not only was it small, it was about equal to a constant times x minus a, and that's what we used. So differentiability implies continuity, but not the other way around. Why not? We see one example already. Oh, sorry. Any questions about that proof before we move on? Okay. We've got differentiability implies continuity, but continuity doesn't imply differentiability. Here's another one, the function mod x. This is another very nice continuous function. It's got a problem at the origin. Everywhere else it's very nice. It's differentiable away from the origin. It's got derivative 1. So for x greater than naught, f of x equals x, and f prime of x equals 1. That's fine. For x smaller than naught, f of x is equal to minus x, and f prime of x is equal to minus 1, that's fine. But at the origin, you have to do a separate check. You actually have to go back to the limit and see what's going on. And what do you see? You get the limit as x tends to 0 plus of f of x minus f of 0 over x minus 0. That's equal to the limit as x tends to 0 plus. Well, when x is at 0 plus, x is positive. So we're talking x over x, which is equal to 1. But the limit x tends to 0 minus of f of x minus f of 0 over x minus 0. When x is negative, mod x is minus x. So that's the limit as x tends to 0 minus of minus x divided by x, and that's equal to minus 1. So approach it with the two different sides, you get different limits, so the limit does not exist. So it is not differentiable at the origin. Any questions about that example? So by now I hope I've convinced you that there are some issues when it comes to differentiability. Reasonably nice continuous functions can have problems of various different kinds. And if you're discontinuous, then it's hopeless, because we know that differentiability does imply continuity. So if you've got a discontinuity, it's even worse. Now, the next example is much more extreme. It's a continuous function that isn't differentiable anywhere. However, we won't prove that. But if you get Mabel to plot, if you tell it to stop the sum somewhere, just add the first few terms together and ask Mabel to plot it, you'll see that it's a very nasty-looking function indeed, but it's still continuous. And 21, it doesn't matter really what that 21 is as long as it's bigger than 2. So it's just powers of a number bigger than 2. That's enough so that when you try to differentiate it, the 2 to the minus n gets wrecked by this thing that it gets multiplied by. So if you add the first few terms together and ask Mabel to plot it, horrible function. Actually proving that this function is continuous, well, you can check it converges by the comparison test. The fact that it converges to a continuous function. There's something called the Weierstrass M test, which unfortunately we haven't got time to talk about. It's very interesting. Anybody interested in the Weierstrass M test, it's a very good application of uniform convergence because this series gives you an example of uniform convergence to another function, and the limit function has to be continuous. But it's a very nasty continuous function, which fails to be differentiable anywhere on the whole real line. So I won't say more about that except to say ask Maple to plot, say, the sum from n equals 0 up to 4 of 2 to the minus n cos of 21 to the power n pi x. And then maybe try some bigger values, and you'll start to see what sort of, maybe add a few more terms. And see what these functions look like, but they're pretty horrible. And you should be able to convince yourself that they just jump up and down so much in sort of funny little spiky ways after a while that you just about convince yourself that the limit's not going to be differentiable anywhere. You can also find out about Brownian motion, which is another example of something which is continuous but not differentiable anywhere. I won't say any more about that. That's optional details to think about that one. So what I want to finish with today is just reminding you some stuff that you already know. We won't be proving them again. This is from calculus from first year, and you're allowed to assume these results and use them. It's the product rule, quotient rule, chain rule for differentiation. But actually, the chain rule for differentiation is quite hard to prove correctly, and even books get it wrong. There are some nasty traps. So you should look in books for details and see whether or not the books get it right. But fortunately, I'm not asking you to know the proof of the chain rule. So here's what we're finishing with today then. Just a reminder that you can differentiate a sum as the sum of the derivatives. You can differentiate a product as, no, not the product of the derivatives, but using the product rule. And you can differentiate a quotient using the quotient rule. And I hope you've got some way of remembering which way that works. Of course, you mustn't be dividing by 0, otherwise it's hopeless. So g shouldn't be taking the value 0, but as long as it isn't, then you can differentiate using the quotient rule. And then the chain rule, that's for your function of a function. And there's your familiar rule. If you're talking about g of f of x, and you want to differentiate it, then you're going to get g prime of f of a times f prime of a. And from now on, you're allowed to assume the chain rule, the product rule, the quotient rule, and everything you knew from calculus about polynomials, trigonometric functions, all that stuff. You can assume all those from now on. Okay, we'll stop there today.